Hi, this is Mahdi, and I'm presenting our short paper COCO, a correlation coefficient-aware data augmentation system. Given an input data set with limited number of informative features, a target column that represents a machine learning task, and a large corpus of tables, the goal of data enrichment is to enrich the input data set with the most informative features for a machine learning task. There are a large number of available data sets that can be used for this specific purpose. This includes open data and data sources inside organizations. However, these available data sources are very large, and it makes it so difficult to find the most relevant and informative features. As an example, DWTC contains 145 million tables and 870 million candidate columns that potentially can be used to enrich the input data sets. Existing solutions focus only on related features and postpone the task of finding the most informative features to the feature selection phase of the system. However, the number of candidate columns can be very large, and it can lead to efficiency problem in the feature selection part of the system. A heuristic is to use the correlation coefficient to find the most relevant features and filter the irrelevant features in the enrichment process. This experiment shows the average R2 score of the machine learning task for 10 Kaggle data sets. Both of these approaches use DWTC corpus to enrich the data set with additional 50 features. The system represented with the red label enriches the data at hand with the most related features, which means joining with the tables that have the most overlapping values with the input data set. On the other hand, the next approach enriches the input data set with only correlating features. And as you see, the correlating features can be a better and effective way of enriching input data set and the training data set for a specific machine learning task. However, picking the right correlation coefficient is crucial for many tasks. And for most of the tasks, Pearson correlation is not the best choice. In contrast, Spearman's correlation is a rank-based correlation coefficient, which is able to detect nonlinear dependencies between two lists of values. This is very important because current machine learning models are able to find the very complex association between features. Another advantage of Spearman's correlation is its robustness to outliers. Consider the depicted example here with two columns. As you see, there is no clear correlation between area column and calling code column of a country. However, in this example, there is an outlier row that has outlier values in each column. And that's why Pearson correlation is skewed by these outliers and presents a very high correlation value. And on the other hand, Spearman's correlation is very robust to this outlier and shows relatively low correlation value. However, due to the fact that the Spearman's correlation requires the value location of each value in the sorted list, and it requires to sort the values inside the columns, the computational cost of a Spearman correlation is higher than the linear correlation coefficients. And this complexity increases in case of categorical value due to the existence of one-hot encodings. In order to find the dependency between two columns, Spearman's correlation first sort the values inside each column and calculates the ranks based on the location of the values inside the column. And then the linear correlation calculation is carried out. The problematic part of this pipeline is the sorting and then calculating the ranks part. And in case of categorical value, one-hot encoding leads to higher complexity. The goal of this paper is to calculate Spearman's correlation in linear time, and COCO does this through a lightweight index structure. Let's see how COCO built this index in the offline phase of the system. For every available column, the values are sorted and the ranks are generated. And the minimum value, which has the rank equal to 1, is marked and the relative ranks are calculated. A relative rank represents the next greater value in the column. This is very important because the joins here are partial, and if we store the actual ranks instead of relative ranks, partial joins will drop some of these ranks, and that will lead to wrong correlation calculation. And in the end, obtaining the relative ranks, the final index would be generated. In the final index, each value represents the location of the next greater value. For example, the next greater value than the minimum value is located in the row number 0, and the next greater is in this third row, and so on. In the online phase, COCO undergoes 3 steps. First, discovering the most joinable tables, or the tables with the highest overlap with the input dataset. We do this through a single SQL query in an in-memory and parallel database system. In the next step, COCO generates join maps. A join map maps the joinable rows inside the input dataset and the candidate joinable table. And finally, the correlations are calculated and the most correlating features are used to enrich the input dataset. As an example, the join map of the input dataset on the left-hand side and the joinable tables shown on the right-hand side is depicted here below. As it's shown in this example, the second row of the joinable table is joinable with this third row of the input dataset. Consider that we would like to calculate the correlation between the column population and the candidate column area. In order to calculate the correlation between these two, we need to first find the rank values of the area column in the candidate table. On the right-hand side, the join map of the candidate table is shown along with the index generated by COCO for this specific column. Starting with the rank 1, COCO starts from the minimum value. And if there is a join candidate from the input data set to the candidate table, this rank is assigned to the corresponding row value. And then the rank is increased and COCO follows the index. If there is no candidate joinable row, the algorithm follows the index without increasing the rank. COCO traverses through the index once and calculates and obtains the ranks in linear time. And obtaining these ranks, now we can calculate the correlation in linear time. We conducted 4 sets of experiments, and we're reporting 2 of them here. In the first experiment, we used World City dataset with 3 million instances as the input dataset and the population column as the target column. We leveraged EDBT as a corpus of tables here. In this graph, we compare COCO with SBE, which is an enrichment system that calculates the ranks by sorting the values in the online phase. As you see, increasing the number of instances in the input dataset, the average runtime for correlation calculation per column increases drastically for SBE. Where for an input dataset with 1 million instances, the average runtime for calculating one single correlation for SBE is 118 seconds, where this number for COCO is 11 milliseconds. This shows the scalability of COCO with respect to the size of the input dataset. In the second experiment, we leverage 100 random data sets with random targets from US, UK, and Canada open data corpus. This graph shows the collective runtime of correlation calculation for all candidate columns. As it's shown, COCO performs better and requires 50% less time to enrich the input data sets compared to SBE and another state-of-the-art approach that applies a coarser grain technique to skip the joinable tables with minimum information loss. Thank you.